We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system.
3I Atlas is now officially the third interstellar object ever observed after 1I ʻOumuamua in 2017 and 2I Borisov in 2019. Unlike Oumuamua's bare comet-like acceleration without a visible coma, or Borisov's hyperactive but otherwise familiar behavior, Atlas developed a distinct coma and tail, yet behaved in ways that defied expectations. Its trajectory was unmistakably hyperbolic, meaning it is not bound to the sun's gravity and will eventually escape back into interstellar space. But along the way, it has given researchers a rare chance to probe the physics and chemistry of material born around another star. But wait, there's more. Recently, 3I Atlas has shifted orbit against gravity, and gas alone can't explain it. 3I Atlas: physical and chemical properties. The size of 3I ATLAS has been a subject of debate since its discovery. Its nucleus has yet to be directly resolved because of its distance and the surrounding coma of gas and dust. Estimates range from something comparable to a large city block to an object the size of a small mountain, likely spanning several hundred meters across. For context, Oumuamua was estimated at 100 to 400 meters in length, while Borisov was closer to a kilometer. 3I Atlas therefore appears to fall somewhere in between. Its mass and volume are still under refinement, but astronomers agree that it is a significant object. The composition of 3IATLAS is perhaps its most striking feature. Using JWST's near-infrared spectrograph, or NIRSPEC, astronomers detected that the coma surrounding the nucleus is overwhelmingly dominated by carbon dioxide. Measurements indicate that carbon dioxide is present at concentrations about 8 times higher than water vapor, which runs counter to the pattern observed in most solar system comets, where water ice is typically the dominant volatile near the sun. This may not seem like a big deal, but it's huge. This unusual abundance points to the object forming in an environment far colder than the one in which most of our comets originated, possibly in the distant reaches of another planetary system's Kuiper belt-like reservoir. In addition to carbon dioxide, JWST also detected smaller amounts of water vapor, carbon monoxide, and carbonyl sulfide. The latter is rare, but has been detected in some comets, and its presence in 3I Atlas strengthens the idea that interstellar objects carry chemical signatures that can preserve information about their natal disks for billions of years. The heavy dominance of carbon dioxide suggests that the temperature and radiation environment of the birthplace of 3I Atlas was markedly different from our own. In the outer reaches of our solar system, beyond Neptune, water ice can remain stable, but carbon dioxide is not usually retained in such quantities. For 3I Atlas to have this much frozen carbon dioxide, it likely formed in a region colder and more distant from its star than our Kuiper belt, or perhaps in a protoplanetary disk where carbon dioxide condensation was more efficient. This insight gives astronomers an opportunity to test models of planetesimal formation under varying stellar and chemical conditions, allowing them to compare how different stars and their surrounding dust clouds might create cometary bodies. Another unusual property of 3IATLAS is how early it became active. Activity in comets is typically marked by the formation of a coma and a visible tail, triggered when the sun's heat causes volatile ices to sublimate and release dust and gas. For solar system comets, this process generally begins closer to the orbit of Jupiter or within the asteroid belt. In the case of 3I Atlas, activity was first detected while it was still far beyond Jupiter's orbit, at heliocentric distances where water ice would not normally sublimate efficiently. The early onset of a coma is consistent with carbon dioxide sublimation, since carbon dioxide vaporizes at much lower temperatures than water. This helps explain why a diffuse cloud began forming so far out, but it also highlights the very different chemical behavior of this comet compared to those we are familiar with. Beyond size, composition, and activity, the polarization of light reflected and scattered by 3I ATLAS's dust has given researchers another unexpected clue. Polarimetry studies measure how sunlight scatters off dust particles, revealing details about their composition, size distribution, and surface structure. In the case of 3I ATLAS, astronomers found unusually deep negative polarization, meaning that the scattered light is polarized in a way not commonly seen in comets of the solar system. Instead, the polarization resembles what has been observed in some trans-Neptunian objects, bodies that orbit beyond Neptune and remain relatively unaltered since the solar system's formation. This similarity raises the possibility that the dust grains in 3I ATLAS are more compact, darker, or differently structured than typical cometary dust, hinting at either a different accretion process or a longer preservation in cold, radiation-shielded environments. The fact that it matches trans-Neptunian objects also provides a bridge of comparison between our distant icy bodies and those from other star systems. These physical and chemical characteristics make it unlike either of its two predecessors, Oumuamua and Borisov. Oumuamua had no detectable coma and exhibited unexplained acceleration. Borisov behaved more like a classical comet, with water-driven activity and a structure similar to long-period comets from the Oort cloud. 3I Atlas, by contrast, blends traits we have never seen combined before. It is clearly a comet with a visible coma, but the chemistry is unusual. The activity began much farther from the Sun, and the dust properties echo the distant edges of our system rather than the comets we know best. The study of 3I ATLAS's physical and chemical properties is ongoing, and its approach to perihelion in late October 2025 will allow astronomers to collect more precise data. Instruments like JWST, the Hubble Space Telescope, and ground-based observatories will continue tracking changes in its composition and activity. Measurements of isotopic ratios in its gases may eventually reveal even more about the stellar nursery it came from, potentially allowing scientists to link its origin to particular types of stars. The rapid advancement of observational technology that has coincided with the arrival of 3I ATLAS is also very impressive. Oumuamua passed by too quickly and was discovered too late for detailed spectroscopic studies. Borisov provided some data, but its proximity was less favorable for high-resolution analysis. With 3I Atlas, astronomers had warning months in advance, and telescopes like JWST were well positioned to provide data across multiple wavelengths. So, what is so odd about our visitor's orbit? Orbital anomalies and debate. It was clear from the start that 3I Atlas was not bound to the Sun's gravity and would eventually leave the solar system after its brief visit. Yet, within weeks of detailed monitoring, reports began circulating that its orbital motion was not conforming precisely to predictions derived from pure gravitational dynamics. Instead, it appeared that 3I ATLAS had shifted its orbit in subtle but measurable ways. The basic mechanism behind orbital changes in comets is well known. As comets approach the Sun, volatile ices, such as water, carbon monoxide or carbon dioxide, sublimate and escape through jets on the surface. These jets act like tiny thrusters, imparting momentum that can slightly alter the trajectory of the nucleus. In the case of most solar system comets, such non-gravitational accelerations are modest, and their effects can be modeled fairly reliably. For example, Halley's Comet shows measurable shifts in its perihelion timing due to outgassing forces, and NASA's Deep Impact mission in 2005 measured jet-induced changes on Comet Tempel 1 with high precision. The expectation then was that 3I Atlas would display similar non-gravitational behavior, scaled to its volatile content. However, the first orbital refinements from tracking data suggested something more unusual was occurring. Observers reported that the magnitude of the orbital deviation was larger than what standard gas-driven models predicted. The implied change was significant enough to raise doubts about whether normal sublimation could account for it. In comet dynamics, this kind of shift typically demands strong directional jets operating consistently over weeks or months. Yet imaging and spectroscopic observations indicated that the gas emission from 3I Atlas S was not especially focused or jet-like, but diffuse. Moreover, while typical comets produce tails that extend away from the Sun due to radiation pressure acting on dust and ionized gas, 3I Atlas displayed diffuse outflow that seemed to project ahead of its direction of travel, rather than trailing behind in a simple anti-solar geometry. Photometric studies showed that the coma extended asymmetrically, almost as if material was being pushed in the leading direction of motion. This is difficult to reconcile with ordinary sublimation processes, which should release gas isotropically, or at least in directions controlled by localized jets on the sunward side. The effect suggested either unusual gas dynamics or an external factor influencing how the material dispersed. One line of explanation being considered is the extraordinary abundance of carbon dioxide in the object's composition. JOST spectroscopy showed that carbon dioxide levels in 3I Atlas were about 8 times higher than water vapor, making carbon dioxide the dominant driver of activity. Since carbon dioxide sublimates at much lower temperatures than water, jets could activate at far greater distances from the Sun, producing non-gravitational forces well before perihelion. If the carbon dioxide outgassing were unusually anisotropic, perhaps concentrated in specific surface features, then the resulting momentum could in principle produce stronger than expected orbital shifts. Still, the diffuse nature of the emission weakens this explanation. Some researchers have pointed out that solar wind and radiation pressure might be playing a role beyond what has been factored into existing models. Radiation pressure is already known to deflect comet tails and affect small dust grains. But in the case of ʻOumuamua, it was also invoked as a potential explanation for its unexplained acceleration. A similar hypothesis could apply to 3IATLAS. Avi Loeb, the Harvard astrophysicist who argued that ʻOumuamua might have been an artificial probe or fragment of alien technology, has suggested that 3IATLAS also deserves scrutiny for non-natural explanations. Loeb has pointed to the unusual forward-directed emission and the scale of the orbital shift as potential indicators that conventional cometary physics may not be sufficient. He has publicly argued for NASA and other agencies to prioritize monitoring the object, including the possibility of using spacecraft like Juno or Mars Reconnaissance Orbiter to conduct flyby observations. He has even gone as far as to suggest that 3IATLAS could shed small mini-probes that might manifest as unidentified aerial phenomena. Mainstream astronomers have been quick to emphasize that extraordinary claims require extraordinary evidence. Many argue that while 3IATLAS is certainly unusual, there is no need to invoke artificial explanations when natural mechanisms, though imperfectly understood, can still plausibly account for the observations. They point out that every interstellar visitor so far has defied expectations in different ways. ʻOumuamua lacked a coma and accelerated oddly. Borisov was hyperactive and fragmenting, and now 3I Atlas is dominated by carbon dioxide and behaving oddly in its orbital dynamics. Then there's the difficulty of interpreting limited data from fast-moving, transient objects. By the time anomalies are recognized, opportunities to deploy new instruments or missions are often lost. In the case of 3I Atlas, however, astronomers had an advance warning. The comet was discovered months before its perihelion passage in October 2025. This has allowed coordinated campaigns using JWST, Hubble, and ground-based observatories across Chile, Hawaii, and Spain to capture data at multiple wavelengths and from different angles. Orbital refinements will continue as it moves closer to the Sun. What is clear is that 3I Atlas has once again forced astronomers to question their assumptions about small bodies from other star systems. The orbital anomalies suggest that our models of gas-driven forces, though robust for solar system comets, may not capture the full range of possibilities in interstellar space. Now, let's look at Loeb's work in more detail. Avi Loeb's hypothesis. Loeb first rose to wide public attention in 2018 when he published a controversial paper with Shmuel Bialy in the Astrophysical Journal Letters, suggesting that ʻOumuamua, the first known interstellar object, might not have been a natural comet or asteroid, but instead a thin, possibly artificial structure propelled by radiation pressure. He elaborated on this view in his 2021 book, Extraterrestrial, the first sign of intelligent life beyond Earth, in which he argued that mainstream science was too quick to dismiss the possibility of extraterrestrial technology. Many astronomers disagreed, pointing instead to natural explanations such as a hydrogen iceberg or a fragment of a nitrogen ice body, but Loeb insisted on keeping artificial origins in the conversation. In public interviews and commentary following the July 2025 discovery, Loeb suggested that three IATLAS's unusual orbital behavior should not be automatically attributed to exotic natural processes. He pointed out that the diffuse outflow ahead of the object, unlike the trailing tails of typical comets, was especially curious, and that the magnitude of its orbital shift implied a significant transfer of angular momentum. To Loeb, these features warranted consideration of the possibility that three IATLAS might not be a standard comet at all. He proposed that it could be a technological artifact, perhaps a fragment of interstellar debris, intentionally or unintentionally released by another civilization. He also speculated that if such objects shed mini-probes or fragments during their passage through the solar system, they might appear as UFOs when observed in Earth's atmosphere. Loeb has urged the scientific community, and NASA in particular, to devote closer surveillance to three IATLAS while it remains within observational reach. By mid-2026, the comet will begin fading from detectability as it recedes beyond Saturn's orbit, which leaves a limited window for close study. Loeb has suggested repurposing existing spacecraft already in the inner solar system for opportunistic observations. Among the candidates he mentioned are NASA's Juno spacecraft, which orbits Jupiter, and the Mars Reconnaissance Orbiter, which has a versatile suite of imaging instruments. Though neither mission was designed for interstellar comet flybys, Loeb argues that redirecting or supplementing their observational programs could provide invaluable close-range data on three IATLAS's structure, composition, and activity. He has also reiterated his broader call for a dedicated interstellar object intercept mission, something that the European Space Agency's proposed Comet Interceptor, whose launch is scheduled for 2029, could potentially fulfill for a future visitor. Most astronomers, however, remain skeptical of Loeb's more provocative claims. The consensus view is that while three IATLAS is certainly unusual, its properties can be explained within the framework of natural astrophysical processes once the right combinations of chemistry, dust physics, and environmental conditions are taken into account. They note that interstellar comets originate in star systems that may have entirely different planetary formation histories from our own, and that chemical abundances can vary significantly. The dominance of carbon dioxide, for example, suggests that 3I Atlas formed in a particularly cold environment where water remained locked in ice while carbon dioxide was more mobile. In such a setting, strong and asymmetric carbon dioxide jets could drive orbital perturbations unlike those seen in solar system comets. Polarization studies show that dust properties in this case are similar to those of trans-Neptunian objects. While Loeb insists that artificial origins should remain on the table, most researchers counter that no direct evidence currently supports such an interpretation. All confirmed measurements, such as spectral data, coma activity, and orbital dynamics, are still consistent with unusual but natural processes. For instance, dynamical models that incorporate extreme carbon dioxide sublimation have already reproduced some of the observed trajectory shifts. Similarly, simulations of solar radiation pressure acting on unusually small and reflective dust grains, can account for additional acceleration. Invoking extraterrestrial technology, for some experts, is not yet necessary. However, Loeb argues that science has historically advanced by entertaining the improbable. He often draws attention to the fact that our understanding of interstellar comets is based on only 3 examples, which hardly constitutes a representative sample. In his view, dismissing the possibility of artificial origins outright is premature. The history of astronomy is full of cases where seemingly outlandish explanations turned out to be correct. From the recognition of meteorites as extraterrestrial stones in the early 19th century, once ridiculed as peasants' tales, to the discovery of pulsars in 1967, which were initially dubbed LGM for Little Green Men because of their unnervingly regular signals. In Loeb's estimation, 3I Atlas deserves the same open-minded consideration, even if the odds are slim. Supporting his stance is a wider context of unexplained aerial and space phenomena. The US Department of Defense, for instance, released in 2020 and 2021 several declassified videos showing UFOs captured by Navy pilots. While many of these cases remain unresolved and could yet be attributed to natural or terrestrial causes, they demonstrate that the scientific community has documented anomalies in the skies that defy conventional explanation. Loeb has even argued that if advanced extraterrestrial probes were operating in our solar system, they might appear precisely in such ambiguous forms. He also points to physical materials that, in his view, could be indicative of non-natural origins. In 2014, a meteor dubbed CNEOS 2014-0108 entered Earth's atmosphere near Papua New Guinea. Loeb, working with the US Space Command, confirmed that the meteor's speed and trajectory marked it as an interstellar object, predating even ʻOumuamua and Borisov. In 2023, during the Galileo project's expedition to the impact site, Loeb's team retrieved tiny spherules from the seafloor. Preliminary analysis suggested unusual alloys, including high concentrations of iron, silicon, magnesium, and trace elements arranged in ways not commonly found in terrestrial or solar system meteorites. Loeb interprets them as potential evidence of advanced manufacturing, or, at the very least, exotic astrophysical processes we do not yet fully understand. For him, 3I Atlas offers another opportunity to investigate. The philosophical backdrop to Loeb's arguments is the Fermi paradox. If intelligent life is common, why has Earth not encountered obvious signs? One possible answer is the zoo hypothesis, which suggests that advanced civilizations may deliberately avoid overt contact, observing us at a distance the way humans watch animals in a reserve. Under this framework, interstellar objects like 3I Atlas could conceivably serve as surveillance devices, just as military radars often misclassify reconnaissance drones as flocks of birds. Humanity may be misclassifying alien probes as natural comets. 3I Atlas, regardless of its ultimate interpretation, is already proving invaluable for expanding knowledge of cometary diversity. Its unique chemical profile provides a direct sample of the volatile inventory of another star system, something that cannot be inferred from remote observations alone. Its orbital behavior tests the limits of existing comet dynamics models, forcing researchers to refine their understanding of how non-gravitational forces operate under extreme conditions. The comet's unusual polarization properties add to the growing evidence that interstellar dust can differ significantly from what we find in the solar system. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.